60 degrees Celsius. That's not the temperature of the air. That's the temperature of the road under your feet. In some cities, the asphalt gets hotter than the surface of Venus at night. Hot enough to cook an egg. Hot enough to melt the soles of shoes. Hot enough to turn a solid highway into something that moves like syrup. Every summer, in dozens of countries, roads don't just get warm. They fail. They crack open. They ripple like waves frozen in place. In some places, cars have literally sunk into the pavement. For decades, engineers believed they understood heat. They believed they understood asphalt. They believed they had this problem solved. But the story of why roads melt is far stranger, and far more dangerous, than anyone expected. At first, the explanation seems obvious. It's summer. The sun is strong. Roads are dark. Dark surfaces absorb heat. So the road gets hot, and hot asphalt gets soft. Simple. That's what most people believe. That's even what most news reports say when a highway buckles in the middle of a heatwave. But here's the problem. Roads are engineered to survive heat. Asphalt is specifically designed and tested to handle high temperatures. Every major highway goes through rigorous heat resistance testing before it's ever open to traffic. So if roads are built to handle heat, why are they still failing? The real answer isn't just about how hot the air gets. It's about something happening inside the road that almost nobody thinks about. Imagine standing on a highway in the middle of July. The air temperature says 40 degrees Celsius. Uncomfortable, but survivable. Now imagine shrinking down, small enough to slip beneath the surface of the asphalt itself. Down into the black layer that vehicles roll over every single day. Down here, the temperature isn't 40 degrees. It's 65. Sometimes higher. Because asphalt doesn't just sit in the sun, it becomes a heat trap. Dark surfaces absorb almost all incoming solar radiation instead of reflecting it. And unlike open ground, a road has nowhere to release that heat quickly. It just keeps building, layer by layer, hour by hour. By early afternoon, the surface has absorbed hours of concentrated sunlight with almost no way to cool down. This is the moment engineers call the danger zone. And this is where the Real story begins. In the early 2000s, transportation engineers in the United Kingdom noticed something strange. Roads that had performed perfectly for years, roads built with modern, heat-tested asphalt, were suddenly buckling in weather that wasn't even considered extreme. At first, they assumed it was a construction flaw. Bad materials. A batch of poor-quality asphalt, maybe. So they tested the roads again. The materials were fine. They tested the drainage systems, thinking water damage might be weakening the structure underneath. That wasn't it either. Then they looked closer, not at the road's surface, but at its molecular behavior under extended heat exposure. And what they found changed how engineers think about roads forever. Asphalt isn't just black rock. It's a mixture of aggregate, stone, sand, gravel, held together by a binder called bitumen. Bitumen is the key to everything. At normal temperatures, bitumen acts almost like a solid glue, locking the stones together into a strong, stable surface capable of carrying tons of weight. But bitumen has a weakness. It's a viscoelastic material. That means, unlike pure solids, it behaves differently depending on temperature. At low heat, it's rigid. At moderate heat, it flexes. But past a certain threshold, it starts to behave like a thick, slow-moving liquid. Engineers expected roads to soften slightly in extreme heat. That was normal and accounted for. But what they discovered was that repeated heat cycles, hot days followed by hot days followed by more hot days, cause the bitumen to slowly rise toward the surface. This process has a name. Binder migration. And it explains something that had puzzled road crews for years, a strange, glossy sheen that sometimes appears on a highway just before it fails. But binder migration alone doesn't explain why some roads survive brutal heat waves without a scratch, while others fail in relatively mild summers. Something else was going on. And when engineers finally traced the pattern, they found something almost nobody had considered. It wasn't just about heat. It was about traffic. Here's where the story gets dangerous. A road sitting empty under the sun heats up, but it stays relatively stable. The real problem begins when heavy vehicles start driving over it. Picture a fully loaded truck, tires pressing down with immense force onto asphalt that has already softened from hours of direct sun. Each time a tire rolls over a weakened section, it pushes the softened bitumen sideways. Not evenly, not predictably. It shoves the material toward the edges of the tire path. One truck barely makes a difference. But multiply that by thousands of vehicles, hour after hour, across a single stretch of highway during a heat wave, and the road begins to shift beneath the traffic that depends on it. This is called asphalt rutting. And when conditions become extreme enough, rutting turns into something far more violent. Concrete roads face a different but equally dangerous version of this problem. Unlike asphalt, concrete doesn't soften, it expands. Every concrete road is built in segments, called slabs, with small gaps between them called expansion joints. These joints exist for exactly this reason, to give the concrete room to grow when it heats up. But during extreme, prolonged heat, concrete can expand beyond what those joints were designed to absorb. When that happens, the slabs have nowhere left to go. They push against each other with tremendous force. And when the pressure becomes too much, something has to give. The road doesn't just crack. It explodes upward, sometimes violently, creating a sudden ridge or spike in the middle of a highway. Engineers call this a blowup. Drivers call it terrifying. There have been documented cases of concrete slabs bursting upward by more than 30 centimeters in a matter of seconds, enough to flip a fast-moving vehicle without warning. For road crews, summer isn't just uncomfortable. It's a battle against time. In extreme heat regions, some highway maintenance teams now work through the night, avoiding daylight hours entirely. Not out of convenience, out of necessity. One veteran road engineer described watching a section of newly laid asphalt begin to shimmer and shift under the afternoon sun, forcing his crew to halt work immediately and rope off the area before it became a hazard to their own equipment. Pilots have reported something even stranger, small aircraft unable to safely land or take off because runway asphalt had softened enough to risk their landing gear sinking in. Airports in extreme heat regions have had to cancel or delay flights, not because of storms or visibility, but because the ground itself had become too soft to trust. At this point, it seems like the story is simple: heat softens roads, heavy loads destroy them, and buckling is the dangerous result. But there's a deeper mystery still unanswered. Why do some roads, built decades ago, using older technology, survive brutal summers without failing? And why are newer roads, built with modern engineering, sometimes the ones that fail first? The answer forced engineers to reconsider everything they thought they knew about road design. The uncomfortable truth is this: modern roads are often designed for the climate of the past, not the climate of today. Asphalt mixtures are engineered based on historical temperature data, decades of past weather patterns used to calculate exactly how much heat a road need to withstand. But global temperatures have shifted. Heat waves that used to be rare events are now becoming regular occurrences. Peak surface temperatures are exceeding the thresholds that roads were originally designed for. In simple terms, many roads across the world were built for a version of summer that no longer exists. Engineers now use a grading system called performance grade, or PG, to classify asphalt binders based on the exact temperature range they can survive. A road rated for a PG 64 binder, for example, is engineered to remain stable up to 64 degrees Celsius on the surface. The problem is that surface temperatures in many regions are now regularly exceeding those historical design limits, sometimes by more than 10 degrees. Which means, quite literally, thousands of kilometers of road infrastructure around the world are being pushed past the exact limits they were engineered to survive. This isn't a rare, freak occurrence. It's becoming the new normal. Once this pattern became clear, engineers didn't just accept it. They started rethinking the very chemistry of asphalt itself. New binder formulas are being developed using polymer-modified bitumen, materials engineered to stay stable across a far wider temperature range than traditional binders. Some countries have begun experimenting with reflective road coatings, lighter-colored surface treatments that reduce how much solar heat the asphalt absorbs in the first place. Others are testing entirely new pavement technologies, permeable surfaces designed to allow heat and water to pass through more efficiently, reducing the intense heat buildup that leads to binder migration. In Australia and parts of the Middle East, regions that have dealt with extreme heat for generations, engineers have developed specialized high-temperature asphalt blends capable of resisting rutting even in surface temperatures above 70 degrees. But rolling out these solutions across entire countries takes years. Sometimes decades. Which means, for now, the danger hasn't disappeared. It's simply being managed, road by road, heatwave by heatwave, step back, and the scale of this problem becomes almost impossible to comprehend. There are more than 64 million kilometers of paved roads on Earth. Every single one of them is exposed to the sun. Every single one of them is aging. And every single one of them is now facing a climate that is shifting faster than most infrastructure was ever designed to handle. A road that performs perfectly today could become unstable in 15 years, not because it was poorly built, but because the world around it changed. This isn't just an engineering problem anymore. It's a race against a warming planet. We drive over roads every single day without a second thought. We trust them completely, trust that the ground beneath our tires will stay solid, stay predictable, stay still. But beneath that black surface is a constant, invisible battle between heat, pressure, chemistry, and time. A battle most of us will never see, until the one day the road beneath us decides it can't hold on any longer. The things we walk on, drive on, build our entire lives around, are often far more fragile, and far more complex, than we ever imagined. And maybe that's the real lesson hiding underneath the asphalt. The ground we trust the most is sometimes the ground we understand the least.